of boundaries.
Okay. Hold on. Okay, I'm going to share my screen. Give me 1 second here. Oh, I have to tell it it's okay that it's being live streamed. Got it. All right. Okay, let me share my screen. Yes, everybody see that? Okay, so see if I can get rid of my picture in the corner here. Oh no, don't do that. I'm sorry. How do I undo that? Oh, sorry. I tried to get rid of my picture. Instead, it got rid of what I was doing. Sorry about that, guys. Okay, yeah, I guess I have to leave my picture up in the corner there. All right, well, thank you. So welcome to A Week at Infinity. And since I'm the first talk today, I thought I'd give a sort of an overview of some of the ideas that are going to be talked about this week and a little bit of the history. So this is going to be just a sort of expository talk to try and put everything into context. Okay, so what are we going to, so in other words, in this talk, we're going to head for infinity. So let's start with the question that most of the topic is going to be about boundaries of geodesic metric spaces. So the first question is, what do we mean by a boundary? So most of us, when we first encounter the notion of a boundary in mathematics, it's a boundary of some, say, subspace of a topological space. And the boundary is defined to be the, let's see if this works. It's defined to be the of the subspace U, you would take the closure of U and remove the interior. So it's the sort of the edges of this subspace U. Or maybe we learned about boundaries of manifolds, and a boundary of a manifold, well, you know, what's a manifold? A manifold is a point where every point has a neighborhood that looks like Rn, but maybe it has some points where a neighborhood looks like just half space in Rn, and those are the boundary points. Those kind of boundaries are kind of limits, a point where you can't go any farther. It's like a fence. You run into something and you have to stop. But what we want to talk about today is absolutely not these kind of boundaries, but rather directions we can travel in a space where there are no stopping points, where we can go and go and go and go all the way out to infinity. Okay. And the boundaries we're going to be talking about are going to encode this idea of what are all the ways we can go out towards infinity. Okay. All right. So these are boundaries at infinity, if you'd like. All right. So there are two sort of approaches to this, which we'll be hearing about in the two mini courses this week, and as well in many of the individual lectures. So one way, I'm standing in my space, I have some space X and I'm standing in my space X and I want to travel to infinity. Well, one way to do that is to sort of head out to infinity as fast as possible, that is along a geodesic ray. So we take a straight line, a geodesic ray, and head out and out and out and out. We assume our space is non-compact, that we can just keep going and going and going. And this, for example, a good model of this would be the hyperbolic plane. We might start at some base point x0 and look at all the ways we could head out towards infinity, because in the hyperbolic plane, I guess the model I'm using here is the Poincare disk model of the hyperbolic plane. The distances get farther and farther the farther out you go, so you're never going to actually reach the boundary there. You're never actually going to reach the circle. Okay, so that's one way to travel to infinity. And the idea is to create a boundary, which in this case, in the hyperbolic plane case, would be exactly what you expect. namely, it would exactly be this disk at infinity, because all the different ways to travel to infinity are encoded in that disk. Each point in the disk gives you a different way to travel to infinity. Okay, so another way one could ask about going to infinity is by random walks. All right, and a random walk, we might be, say, we're on a graph, maybe a Cayley graph or something, and we start at some point, and then we randomly choose a direction to go in that graph, and we wander around, and we can ask, are we heading towards infinity or are we not heading towards infinity? And with what frequency and which areas of infinity are we heading? Okay, that gives rise to a notion of a boundary, which is measure theoretical. As opposed to a topological space, we get a measure space, a measure theoretic boundary known as the Poisson boundary. Okay, so there are these two kind of different ways of thinking of traveling towards infinity, and we're going to be hearing about each of these in mini courses, and probably even more interesting, it turns out there are connections between these that we're going to also hear about. Okay, so we've got, for today's talk, since I don't know that much about random walks, I'm going to mostly focus on the left side of this picture, on topological boundaries. And I want to tell you sort of the history of the development of some of these ideas. So there are topological boundaries, and I'll go into this in detail in the talk. Were first introduced for hyperbolic spaces. Then, more recently, the notion of a hyperbolic boundary was expanded to more general spaces using something called the Morse boundary. And then finally, what we're going to hear about in Khosrow's mini course is a modification of the Morse boundary called the sublinearly Morse boundary, which has some nicer properties. So what I want to tell you about is kind of the development of those ideas and how they differ. All right, so I'm just going to give you an overview, very little technical detail, just kind of a big picture. Okay, any questions so far? All right. Oh, yes, there are lots of other boundaries that I haven't mentioned. I don't know if we'll hear about them this week or not, but there's a roller boundary, a simplicial boundary, a Furstenberg boundary, et cetera, et cetera, et cetera. There are lots of different variations on these, depending on the sort of structure of the space you start with, but I'm not going to be talking about those. All right, so first, before I jump into the history, why do we care about boundaries anyway? Well, there are many reasons. One reason people sometimes want to put a boundary on a space is to compactify it. So, for example, the hyperbolic plane is non-compact; it goes on forever. But if we put this circle at infinity, then that compactifies the plane and allows us to work with a compact space. Similarly for manifolds, sometimes we want to compact, we have a non-compact manifold, we want to compactify it. Well, we might be able to do that by putting a boundary at infinity. So that's one reason. Another important one is studying the dynamics of an isometry. So if I have an isometry that takes X to itself, we can ask, just start at some base point or at any point you want. And what happens if I apply that isometry over and over and over again? What happens to those points? Do they just go wander around in a circle? Do they head out to infinity? How do they behave? So the behavior of isometries when they're applied over and over and over again often can be encoded in terms of this boundary. Finally, just generally in geometric group theory, we're interested often in understanding what I call the large scale geometry of a group. And it turns out boundaries, one can define, as we'll talk about later, one can define, in many cases, the boundary of the group, which encodes certain aspects of its large scale geometry. So, we'll see some of these ideas in more detail as the talk goes on. So there are lots of reasons why boundaries are useful. Okay, so now let's get into a little more concrete details. I'm going to start with some terminology that I hope everybody knows already because I can't go into it in detail, but here's some words I'm going to sort of assume you know, because I'm going to refer to them as we go along. The first is has to do, let me say right from the beginning that I am going to assume throughout this talk that X is a proper geodesic metric space. Proper means closed balls are compact. I don't really need that for most of this. If you want to drop it, but a few technical things that I don't want to have to get into technical points. So we don't, geodesic metric space is the important thing. Proper is not the essential here. It's just convenient. Okay, so, and that's throughout the talk. All right, so we will be particularly interested in metric spaces which have some kind of nice curvature property, at least at the beginning. We're going to require that. And the two standard ones are hyperbolic or delta hyperbolic and cat zero. Hyperbolic being a form of negative curvature, such as the hyperbolic plane, for example, and cat zero being a form of non-positive curvature. Think the Euclidean plane, for example. All right, I'm not going to do formal definitions. I'm hoping everybody's seen these, but basically just have models in your head of like the hyperbolic plane or the Euclidean space when you want to test out ideas. All right, what we do need the formal definitions of, and let's go through these, are quasi-isometries. They're going to be essential to this talk. Okay, so let's actually state the definition of this. So an isometry between two spaces, I have two metric spaces, and an isometry preserves distances on the nose. If two points have distance d in x, then after I apply this isometry f, they still have distance d in y. That's an isometry. Well, we're going to, we want a looser notion, a quasi-isometry. So first of all, let's define a quasi-isometric embedding. So it's a map from X to Y, which doesn't preserve distances on the nose, but it doesn't distort distances by too much. There's a linear function depending on two constants, lambda and epsilon, which control how badly the distance changes. Okay, so it's a linear function, lambda times the original distance plus epsilon, and on the other side, 1 over lambda minus epsilon. Okay, so the distance may not remain the same, but it's not distorted by too much. And at times we will care about the actual lambda and epsilon. So we may refer to this as a lambda epsilon quasi-isometric embedding if we need to know exactly what the constants are. So a quasi-isometric embedding is simply one for which there exists a lambda epsilon, blah, 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 but sometimes we need to know what that lambda and epsilon are. Okay, so a quasi-isometry, which I will just call QI, it requires more than that. Not only does F distort distances by a bounded amount, but it's quasi-surjective. It's almost surjective. Namely, every point in Y is within epsilon of a point in the image. So it sees all of the image sees all of Y more or less. All right. And again, if we want, we may want to specify the lambda epsilon here, depending on the situation. Okay. So QI is quasi-isometry. And the other quasi concept that it's going to come up constantly is the notion of a quasi-geodesic. Well, a quasi-geodesic in X, so a geodesic in X is an isometric embedding of an interval into X. So it's a map from an interval into X, which preserves distances. A quasi-geodesic is a quasi-isometric embedding of an interval into X. So now, and these intervals, I just wrote it as I because they can be finite, they can be half infinite, or they can be bi-infinite, any of those. So we can have infinite geodesics, finite geodesics, whatever. Okay, so those are important concepts in what we're going to be doing. All right, so let's look at a quick example just to keep in mind. A quasi-geodesic. Okay, a geodesic, let's take the plane with the standard Euclidean metric on the plane, okay? So a geodesic is just like a straight line, okay? This is a geodesic ray I've drawn here, half infinite ray. What does quasi-geodesic look like? Well, there are all kinds of quasi-geodesics. For example, it turns out if I make a right triangle of any size, like I could do a bunch of right triangles, I'm going to sort of head out along this way, that any such that the right triangles are let's see, it's the epsilon, it's root 2, 0, are root 2, 0 quasi-geodesics. I leave it to you as an exercise to check that. And the interesting thing is it doesn't matter how big the triangle is. I could have instead gone to here, and then here and here, or I could have gone to here and here, et cetera, et cetera. Doesn't matter how big these triangles are. They're all root 2, 0 quasi-geodesics. So they look less and less and less like the geodesic, the bigger I get. All right, so got to keep that in mind. You'd like to think that quasi-geodesics kind of look like geodesics, but be careful. In fact, there's a really weird one. I wasn't going to do that. I was going to do this later, but let me just throw it in. There's a really weird one in the plane that does this, a quasi-geodesic. It's called the logarithmic spiral, where the distance grows logarithmically. And this turns out to be a quasi-geodesic I've not written down the formula, but there's this logarithmic spiral. So quasi-geodesics in the plane can look pretty weird. So we'd like to think that they kind of look like geodesics, but be careful. That's not always the case. All right. All right. So any questions about terminology? All right. Then let's head for infinity. Okay. So I'm going to talk about, as I said, the development of different concepts of boundaries. So the first one to be introduced in this, I guess, was, well, there were classes, these existed classically for hyperbolic manifolds, for hyperbolic n-dimensional hyperbolic space. They were generalized to delta hyperbolic spaces were introduced by Gromov, and somebody correct me, I believe it was probably Gromov who first introduced this boundary, but I could be wrong. In any case, the original, the sort of first real use of these boundaries, it was, definition and use was for hyperbolic spaces. So we're in a negative curvature situation now, all right? All right, so for this section, I'm assuming now that my space is hyperbolic. All right, for convenience, let's fix a base point, although as I will point out later, the base point's really irrelevant. Any base point will do. And we want to think of the boundary as being ways of heading to infinity. So let's make that a little more precise. So we'll define the boundary, and for a moment, let's take it based at x0 to be set theoretically the set of geodesic rays based at this base point, starting at this base point and just going on forever. All right, a geodesic ray in our space. But it turns out that in a hyperbolic space, geodesics between points are not necessarily unique. You can have multiple geodesics between points, and similarly, rays are not really unique. That is, it's possible to have geodesic rays that stay bounded distance from each other forever and ever. And so we have to impose an equivalence relation here where two rays are considered equivalent if alpha is, it's called the Hausdorff distance is bounded. That is to say alpha stays bounded distance from beta and beta stays bounded distance from alpha. So if they stay always bounded distance from each other, then we'll consider them to represent the same point at infinity. Okay, so that's what the boundary is set theoretically, and now we need a topology on it, and there are a number of ways of defining this topology. I'm going to do it by defining a neighborhood basis of one of these rays. What are the neighborhoods of a given, I fix a ray, and I want to know what are the open neighborhoods of that ray. So the open neighborhoods of the ray are given by, we take a positive real number R, and we look at the other rays that stay close to our given ray alpha for distance R. So we can just take it to be delta close, for example, where delta is the hyperbolic constant. It's delta hyperbolic. So in a hyperbolic space, I didn't really talk about the definition, but we have things have to stay delta close for a long time. They can't get if they're well, they don't have to, but in a triangle, everything is within delta of another side. Okay, so you get these long strings that are delta close to each other. So what we want to look at is rays that stay delta close to each other for distance R. the bigger R gets, the smaller the neighborhood gets, and it converges, we get smaller and smaller neighborhoods of alpha, okay? All right, so we'll take that to be, so just think intuitively that open sets come from looking at rays that stay close for a long time, small open sets, open neighborhoods of alpha. Okay, so it turns out that the base point doesn't really matter. In fact, we could have looked at rays starting anywhere and still made a similar definition. And so we're just going to drop the base point notation. It's just a little easier to think about what the boundary looks like if you started a base point and always go out from that base point. But the base point turns out to be irrelevant, and we'll drop it from our notation. Okay, so let's look at a couple of examples. Well, the most obvious one, the one I've been talking about all along, and we actually already talked about, is the hyperbolic plane. And as I said, a lot of people think of the hyperbolic plane in terms of the upper half space model, but for thinking about a boundary, it's way easier to think about the Poincare disk model, because then the boundary is staring us in the face, because here's my x0, here's my points, etc., and I exactly get what I expect. Namely, the boundary is just the circle and infinity if we use the Poincare disk model. In the upper half space model, the boundary is the real line together with one extra point at infinity, which closes the real line up into a circle, but it's a little harder to picture that one. So I prefer the Poincare disk model here. Okay, here's a more interesting one. Let's start with X is a tree. So a tree is a classic example of a delta hyperbolic space. In fact, it's zero hyperbolic. And we pick a base point. Here's my base point. And we start traveling away from the base point, geodesically traveling away from the base point. And I've chosen to just take valent, a bivalent tree here. But you could do this. You could do this with any tree. All right. Well, I guess I want locally finite tree. All right. So what happens? Well, what's a geodesic ray look like? Well, let's see. Maybe I want to go this way first, and then let's choose this. Oops. And then let's choose this direction and this direction, maybe this, etc. Right? So what am I doing? Well, at each point, to specify a geodesic, at each point, I have to specify left or right. Right? Or if you want, I could specify 0 or 1, 0 or 1, 0 or 1. Pick which direction, right? A side. I have to specify a side. Going all the way to infinity is an infinite sequence of these zeros or ones that tells us left or right, left, right, left, etc. Right? It's an infinite sequence of one of these things. What is that? Well, another way of thinking of it, if I thickened up my edges a little, is that I'm kind of removing the middle third, and I'm choosing the left half or the right half. And then I'm removing the middle third and choosing the left side or the right side, and removing the middle third and choosing the left side or the right side. Guess what? We get a Cantor set. Okay, we get the standard traditional Cantor set. Okay, so it turns out that indeed these are Cantor sets. Even if it's not just two, you can put in more bifurcations. You still get a Cantor set. Okay, all right. So you get an interesting boundary in a case like that. All right. So that's the basic idea. We're literally looking at ways to travel to infinity, and we're encoding all those different ways of traveling to infinity as a topological space. By the way, I didn't write it down, but you can also topologize X union boundary of X. I didn't write it down, but there's a natural way of thinking of the boundary of X union its boundary as a single topological space. All right, it's the definition is very similar. So I'd like to talk about what some of the key properties of these boundaries are. There's a nice survey article by Benakli and Kapovich with a lot more information than I'm giving here. You might want to take a look at that if you'd like to learn a little more about hyperbolic boundaries. All right, so yeah, as I said, I'm only going to mention a few key properties that played a major role in what comes next. So what are those properties? Well, the first thing is that it does give a compactification. I mean, actually, I wrote boundary X is compact, but so is X union boundary X. If you build this space where you glue the boundary onto the original space, you do get something compact, okay? So it does give a compactification of your space. And not only that, the boundary can be given I say a natural metric. It's not unique. There's not kind of a canonical metric, but there's a sort of a class of metrics that can be put on this boundary, which are nicely behaved. So we get this nice compact metric space as our boundary. Okay, another property that turns out to be useful is what I call the visibility property. All right, if I think of geodesics as lines of sight, a geodesic is a line. You can think of light as traveling along geodesics if you want. So we think of a geodesic as a line of sight. So what am I doing? Well, I'm taking 2 points. Let's go back up here to my hyperbolic space where I can see this. So maybe I've got a point here and a point here on the boundary. All right. Well, a priori, those came from 2 different rays, right? But my claim is there's actually a bi-infinite geodesic connecting them. That is, I can find a geodesic that goes from here to here. All right. I can see one of these points from the other point in the sense that there's a bi-infinite geodesic, which allows me to get from one to the other. Right? These 2 rays don't form a geodesic, but there is a geodesic. And remember, this is a hyperbolic space. So actually what I've drawn here, it's got to be a lot thinner than that. It's actually going to go pretty far back, but it's going to be a continuous geodesic. All right. Okay, so that's what's called the visibility property. And that turns out to be useful for all kinds of things. Right. Okay, more properties. All right, I said that one of the reasons we're interested in boundaries is to study the dynamics of an isometry. So let's say I have an isometry, and let's assume it's infinite order. Then we can study what it does to the boundary. So first of all, it's clear that if I have an isometry, either X to X or X to Y, I don't care, between 2 spaces, that takes geodesic rays to geodesic rays, and therefore it takes the boundary of X to the boundary of Y, right? So there's a map, and it's a homeomorphism because the inverse isometry gets you back the other direction. So you've got this map, let's say from X to X, it's an isometry. And so I get an induced map, which I'll call map, it's called G. The induced map on the boundary, I'll call boundary of G. It is a homeomorphism. And we can ask, what are the properties of this induced map? Well, it turns out that it fixes at most 2 points on the boundary. It can fix 0, it can fix 1, or it can fix 2, and that's the only thing it can do. And using that, we get a very beautiful classification of these isometries. If it fixes 0, it's elliptic. If it fixes 1, it's parabolic. And if it fixes 2, it's what's called loxodromic. And these can be described very explicitly for like the hyperbolic plane, for example. There are canonical examples of isometries that do these various things, okay? But this is true for any isometry of any delta hyperbolic space can be classified in this way. So that's very cool. And the last one has to do with quasi-isometries. So I said quasi-isometries were going to be important here. All right, so we're now looking at quasi-isometries as opposed to isometries. So now I have a quasi-isometry. Well, it's obvious that an isometry between 2 spaces induces a map on the boundary. It turns out to be not so obvious that a quasi-isometry induces a map on the boundary, but it turns out it does. So for hyperbolic spaces, it's a fact that, and we'll talk about this in more detail in a few minutes, that any quasi-isometry between 2 spaces induces a homeomorphism on their boundaries. Why this is, from the point of view of geometric group theory, extremely important. So this is called quasi-isometry invariance. And it's extremely important because we would like to define what we mean by the boundary of a hyperbolic group. So what's a hyperbolic group? Well, there's two ways of defining it. It's either a group whose Cayley graph is hyperbolic, or a group which acts properly co-compactly on some hyperbolic space. Well, it turns out any Cayley graph and any hyperbolic space that G acts properly co-compactly on, any two of those are quasi-isometric. So all the different things that G can act nicely on are quasi-isometric to each other. So we can simply define the boundary of G to be the boundary of one of those spaces, like the boundary of its Cayley graph. And it doesn't matter which one we choose. So this quasi-isometry invariance tells us this very important fact, at least if you're a geometric group theorist, that we have a well-defined notion of a boundary for a hyperbolic group. Okay. All right, I threw in one more thing here, which is maybe beyond the realm of this talk, but I just want to mention there is a kind of a partial converse to this theorem. So what this number 4 says is that given a quasi-isometry, one gets a homeomorphism on the boundary. So the converse is, can you go the other way around? Let's say I have two spaces and I have a homeomorphism on their boundary. Does that mean that the spaces were quasi-isometric? Could I extend this to the interior? And there are theorems which say, well, we need some extra hypotheses on this F here. There's something called quasi-Mobius or alternately quasi-conformal. We need some extra hypotheses, but with a little bit of extra information about this homeomorphism, yes, indeed, we can extend it to a quasi-isometry on the interior. And this is important in what are called rigidity theorems and things like that. So in other words, we can learn a lot from just understanding the boundaries. To some extent, they determine the interior of the space as well. Okay. Okay, so I should say there's plenty of other properties. I just picked out the ones that are most relevant to today's discussion. But these are some of the properties that make boundaries particularly useful to us. The fact that they're defined for groups, the fact that they determine the dynamics, et cetera, et cetera. Okay, so these are some really useful properties. Any questions so far? All right, let's keep going. Okay, so far, remember, everything I said here was for hyperbolic spaces. All right, all of these properties, I'm assuming X is delta hyperbolic. Okay, so now what if I want to work with other types of spaces, not just hyperbolic spaces? Well, so the first generalization that people thought about, and an obvious generalization, would be that instead of strictly negative curvature, what if we just asked for non-positive curvature? Could we do the same thing? All right, so now we're going to suppose that X is cat 0, that is non-positively curved, and we'd like to try and define a boundary and understand its properties. Well, it turns out that the definition we gave before works perfectly well. So we again can pick a base point. We can look at all the rays to infinity. We identify two of them if they stay bounded distance from each other, and we define a topology by a neighborhood of alpha is all the rays that stay close to alpha for a long time. Same definition. I could write it down again, but it would be exactly the same as before. Okay. All right, so good. So we have a nice topological boundary that works. It's, by the way, it's usually called, this is called the visual boundary. There are some other versions of this that I think Kim Ruane's going to talk about in her talk, but we're going to stick to this one. So we have a boundary. All right, so now what are boundaries good for? Well, in order to use them for things, we need some properties, right? We have these nice properties that allowed us to apply the boundary to all kinds of questions. So let's go through this list of properties and see if they still hold for cat 0 spaces. Well, the first one was that the boundary was compact and could be given a nice metric. Yes. we're good. That's true in the cat zero case too. The boundary is compact, it's metrizable, it's a nice space. All right, excellent. All right. Second property. The second property was the visibility property. That if I stood at 2 points on the boundary, I wanted to be able to see one point from the other by taking a bi-infinite geodesic. Well, oops, this one. All right, let's see. So we're good on this one. This one fails, and we can see it already in just the plane. Why is that? Well, any bi-infinite geodesic. I'm going to take one through the origin, but it really doesn't matter where, as I said, the base point's irrelevant. I'm going to think in terms of base point being the origin, but any bi-infinite geodesic. Okay, remember, so what we have by the way, what we have at infinity is again a circle because the directions are, one for each point on the circle. Any bi-infinite geodesic always determines antipodal points on the circle, right? Yeah. So for example, if I took this point and this point, there is no way to construct a geodesic that goes between them. It doesn't exist. It doesn't exist in the plane. Yes, everybody see that? Geodesics can only go from between bi-infinite geodesics can only go. Let's get rid of this. It doesn't exist. There's no way to get from. Oops, sorry. There's no way to get from here to here by a geodesic. Okay, so no visibility. Okay, big deal. Visibility is not that important. All right, what about dynamics of isometries? Well, again, weird things can happen. Hello, I just got stuck. Okay, what about dynamics of isometries? Oops, it's again, we've got a problem. So for example, what's a typical isometry from R2 to R2? Well, how about just a translation? Take a fixed vector and translate everything by a fixed vector. So maybe I'm going to translate by like this. I'm going to take every point and translate it. That's my isometry, okay? Okay, granted that moves the base point to a different base point, but as I said, it really doesn't matter what your base point is, all right? What happens if I do that? What happens to, say, a geodesic? Here's my, oops, I should do a geodesic ray. Let me. So I have a point at infinity given by alpha, all right? And I do this translation. Well, translating, if I translate this whole geodesic, I get a parallel geodesic, right? It's just parallel. It's just going to move it over, all right? But parallel geodesics say bounded distance from each other, so they represent the same point at infinity, all right? Two rays that stay bounded distance. Yes, I've moved the base point, but don't worry about that, okay? So they stay bounded distance, meaning they both give you the same direction in the plane, all right? So this translation fixes the entire boundary, all right? It just fixes the whole boundary. It's a non-trivial isometry, which doesn't show up as anything on the boundary. All right, it shows up as the identity. All right, bad news. The worst news comes from the last condition, which was, if we go back, this keeps sticking. The condition that, my iPad's having trouble. The condition of the quasi-isometry invariance. So the last condition was, given a quasi-isometry, I get a homeomorphism on the boundary. And that was essential for being able to define the boundary of a group. All right. Sadly, this fails. All right. And this, the first example of this was a famous example of Croak and Kleiner. I think we're going to hear more about this in Yulan's talk. And it's not even that complicated a space, right? The Croak-Kleiner example is made up, you start with 3 tori, which I've drawn here. All right, these 3 squares, if I glue A to A, B to B, C to C, etc., become 3 tori, okay? It's 3 tori glued together. And the space that of course is finite. So I mean, we want infinite spaces to be able to travel to infinity. So we take its universal cover. And the universal cover, each of these tori is covered, it becomes a plane, and the thing is infinitely big. What Croak and Kleiner showed is that some pretty minor modifications in the metric, if you just change the metric by a small amount, it creates major changes in the boundary. The boundaries are no longer homeomorphic. Okay, so this was the first sort of amazing example of two cat zero spaces or a cat zero space with two slightly different metrics where the boundaries were not homeomorphic. All right, so we have boundaries of cat zero spaces, but they don't satisfy the properties we would like, right? So what do we do? All right, this brings us to our next stage. Well, the first thing we need to do is to understand what goes wrong. I mean, why is it that boundaries behave so much better in hyperbolic space than they do in cat zero space? What is it we've lost? All right, so it turns out what we've lost is something called the Morse lemma, or the Morse property. So I want to talk about that a bit. All right, so here's a key property that works for hyperbolic space and disappears when we get to cat zero spaces. So let's say we have a quasi-isometry, and we'd like to look for, say, an induced map on the boundary. What would we have to do? Well, we would start with a point on the boundary in X. So that's this geodesic, say alpha, that determines a point on the boundary of X. We would apply F to it, which would then give us no longer a geodesic ray, but a quasi-geodesic ray, yes? F alpha is now a quasi-geodesic ray because F doesn't preserve distances on the nose, it only quasi-preserves them. So we apply F, we get a quasi-geodesic ray, and we want to say, oh, that determines a point on the boundary. Well, how does it determine a point on the boundary? Well, what we're looking for to get a point on the boundary is some way to kind of straighten this and say this corresponds to some particular point on the boundary, right? That's what we'd like to do. So we'd like to straighten F alpha to get a point on the boundary. Well, if Y is hyperbolic, then we can always do this. Then we, in fact, have a unique point on the boundary that this converges to. Why is that? It's because of the Morse lemma, which I haven't written out formally, I've written out informally. It basically says for a hyperbolic space, any quasi-geodesic stays bounded distance from, oops, it should just say a geodesic. Let's just say, let's just say from a geodesic. It turns out, of course, that if it stays bounded distance from more than one geodesic, which is possible, then those two geodesics are bounded distance from each other, so they represent the same point at the boundary, right? There might be more than one geodesic, but they're all within bounded distance of each other, so it determines a unique point on the boundary, okay? And this is absolutely key to even defining a map on the boundary, let alone checking its properties, all right? Okay. What if we tried to do this with in the plane, in Euclidean space? Well, I gave you that totally wacko geodesic in Euclidean space that looks like this, for example. That's a quasi-geodesic. What point on the boundary does that converge to? Converges to every point on the boundary. I mean, it doesn't converge. It goes every which way. There's no way to pick a point out that quasi-geodesic converges to, right? And even those other ones that are a little less wacko with those right triangle things, there's an entire quadrant in there that those could converge to. I mean, there's no unique point that those bigger and bigger and bigger right triangle things converge to. There's no way to do this in a cat zero space. Okay, there's no canonical way to do this. All right, not only that, this property actually plays a key role in understanding many of the properties of hyperbolic boundaries. All right, so this is the key property for hyperbolic space that fails miserably in cat zero spaces. All right, okay, so what are we going to do? Well, that led to the next idea in how to build boundaries, namely the Morse boundary. Okay, so we're up to our second class of boundaries. the Morse boundaries. So we're now going to look at very general geodesic metric spaces. You can still assume they're proper if you want or not. It doesn't really matter. But we now want to loosen up. X. I'm not even going to require that X is cat zero anymore. It's just a geodesic metric space, and it turns out that even if it's not hyperbolic itself, it's possible that some of the geodesics are nice. All right. Okay. All of the geodesics may not be nice, but some of the geodesics might behave nicely. All right. So we want to make that precise. And the idea of the Morse boundary is to just grab those geodesics that are nice and forget about the others. That's going to be the idea. All right. So let's make, for this, I need a formal definition. It's really the only formal definition I think I'm going to give here. All right. So to define the Morse boundary, we want to specify which geodesics are nice. And nice means that they satisfy a Morse property. They stay close to, that geodesics, quasi-geodesics stay close to geodesics. So here's the definition. I need to, so, okay, let me say something. So remember I talked about a lambda epsilon quasi-geodesic. The bigger lambda and epsilon get, the worse the quasiness gets, the more crazy the quasi-geodesic can get. So so our controls are going to have to depend on lambda and epsilon. So we start with just a function from the positive reals across the positive reals to the positive reals. All right, these are going to be the lambda and the epsilon, and they're going to give us some constant that's associated to lambda and epsilon. All right, so here, like this, here. So this is just going to be some constant that depends on lambda and epsilon. All right. Okay, so given that, I want to call a geodesic n Morse. So I have you can define this for quasi-geodesics too, but let's just define it for geodesics. It's easier to think about for now. So a geodesic is n Morse if every lambda epsilon quasi-geodesic beta with n points on alpha lies in the n neighborhood of alpha. So that's a lot of words. Let's draw a picture. So I have my alpha. This is a geodesic. And what I want is that for any quasi-geodesic, and that with bounds at most lambda epsilon, that starts and ends on alpha, what I need is that this never gets farther away than n, where n here depends on lambda and epsilon. All right. Okay, so I want to say it stays n close. It stays in an n neighborhood of alpha. It's just that n may depend on how badly quasi this geodesic is. Right? Everybody got that? Okay, so it turns out that's what we need. All right. So more generally, we'll simply say that alpha is Morse if it's n Morse for some n. All right. Sometimes we want to specify the n, sometimes we don't. All right. Okay. Using this, we're now going to define a boundary. So my claim is, as long as we restrict our attention to these Morse geodesics, things start to behave better. All right, so let's define a new boundary that only allows for Morse geodesics. So we do this in two stages. We first define the n Morse boundary of X, where we only allow alphas which are n Morse. By the way, less than these as n grows, these sub boundaries grow, right? So the bigger n gets, the more we're allowed, the more quasi geodesics we're allowed. So we define the n Morse boundary to be geodesics which satisfy this property for a given n, for a given function n. By the way, these functions are called Morse gauges. I don't know that I'll use that word, but for a given n, given function n, we define the n Morse boundary. Okay, it turns out that, and we define, again, same equivalence relation. Two things are equivalent if they stay bounded distance from each other. And what's more, we can define the topology just like we did before for this. In fact, this thing is, in some sense, and Matt, the person to talk to about this, Matt Cordes, could actually be thought of as the boundary of some hyperbolic space. There's a way of reinterpreting this as the boundary of a hyperbolic space. This thing works acts totally like a hyperbolic boundary, all right, if we restrict the n. Okay, but we don't want to restrict the n. That cuts off too much stuff. So we're going to take the Morse boundary. We're going to allow all Morse gauges. We're going to allow them to get bigger and bigger and bigger, and take the direct limit of all these n Morse boundaries. All right, with the direct limit topology. So we've defined a topology on each boundary n. Now we take the direct limit space as n gets bigger and bigger and bigger. Okay, and that is what we call the Morse boundary. So the set theoretically, the points in the Morse boundary are all the rays which are Morse for some n. We don't care which one. Okay, all right. So we first introduced this idea, myself and Harold Sultan, in the context of cat zero spaces. And then Matt Cordes, actually in his thesis, showed that this actually works for all geodesic metric spaces. Can you imagine that in general? Amazing, amazing. That we don't need any restrictions really on our geodesic metric space. Well, I guess we're still assuming proper, but it works for non-proper too. Okay, so we now have a boundary for every geodesic metric space that hopefully has some properties like hyperbolic boundaries. Okay, so before we jump into the properties, let's look at a couple of examples. All right, so all right, our first example, of course, is the case of a cat zero space. Well, let's look at just the Euclidean plane. Oh dear, there are no Morse geodesics whatsoever. There is no bound. Those, those triangles that I was drawing, those right triangles along one of those rays. Yeah, well, there is, you got this ray, and you've got these things are Morse are not more, get farther away. There's another one that's even farther away. They're farther away, farther away, farther away. There's no way to bound how far away the quasi-geodesics get. So bad news, it's empty. There's nothing. Okay. All right. Too bad. How about if X were hyperbolic? What do we get? Well, if X is hyperbolic, then the Morse lemma tells us that there's actually an n for which every geodesic ray is n Morse. That is, the hyperbolic boundary that we defined above is equal to the n Morse boundary, which is equal to the Morse boundary, because you already have everything. You get n that works for everything. Okay, so that's good. So this can really truly be viewed as a generalization of hyperbolic boundaries. All right. So let's do an example which is neither empty nor everything. And this is always my favorite example. I call it the tree of flats. So I take a 2 torus. Oops, that's not what I meant. I take a 2 torus wedge with a circle, right? Yeah, a torus. Oops, that's going to disappear. Wedge with a circle, and I take the universal cover. And in the universal cover, the 2 torus is covered by flats. There are flats, copies of flats, whereas the circle, it becomes just lines. All right, so I have a bunch of lines and a bunch of flats, and they create a tree-like picture of flats. All right, so what does a Morse geodesic look like? Well, we know that geodesics in a plane are not so good. They're dangerous. All right, so it's okay if we're in the plane for a little while, because quasi-geodesic can't get too far away if the geodesic's short. We can't get bigger and bigger and bigger triangles if we only have a little segment in here. But after a little while, we better leave this plane. Otherwise, we're going to be in trouble, and go to another plane. And then maybe we can stay in this plane for a little while and go to another plane. And then maybe we can stay in this plane for a little while and go in this plane and keep going like this. What is the condition that allows it to be Morse? Well, how badly quasi-geodesics diverge entirely depends on how much time we spend in flats. So it turns out that alpha is Morse if and only if it spends a bounded amount of time in each flat. All right, bounded amount of time in each flat. And that bound is what determines n. the bigger, the bigger n gets, the more time I can spend in a flat. But and depending on how long I'm allowed to spend in each flat, that's going to determine n. Well, it turns out that, okay, aside from, if you just, aside from the fact that I spend a little bit of time in this flat and a little bit of time in this flat, if I just collapse those, then what I see is like a tree, basically. The places I can go, it looks kind of like a tree. And indeed, the n Morse boundary is exactly a Cantor set, just like it was in the tree. The Morse boundary, it's a direct limit of Cantor sets. It's a little more complicated, but at least the n Morse boundaries we understand, they are Cantor sets, all right? And they're bigger and bigger Cantor sets as we let n get bigger and bigger, okay? All right, so there's an interesting one. So we can see that there are geodesics that are Morse and geodesics that are not Morse. What we're never, ever going to see, no matter how big n is going to get, we are never, ever going to see geodesics which remain forever in one flat, for infinite time in one flat. Those will never show up here. So the boundaries of these flats will never show up. We can never get to infinity inside a single flat. Yeah, we always have to travel in the tree-like direction after a while. Okay, it turns out actually that this is true. So this is a special case of this space is the Salvetti complex for something called the right-angled Artin group. And in fact, with Matt and Alex Sisto, we studied Morse boundaries of all right-angled Artin groups, and we showed that this basically is what you see everywhere, that the n Morse boundary is always a Cantor set, and that the Morse boundary is a certain kind of what we call an omega Cantor set. It's a certain nice kind of direct limit of Cantor sets in which each Cantor set embeds in a nice way in the next Cantor set, all right? And so we were able to give a complete topological description of all of those boundaries. Okay, so we get some interesting spaces. Questions on the definition? Okay, so we're restricting which geodesics we allow and which ones we don't allow. And other than that, we're building a similar idea for a boundary. Okay, so what was the point? The reason we introduced this is we wanted to get back those nice properties that hyperbolic boundaries had, right? We had lost all these nice properties, and we want to know, can we get them back? And so here are some properties of Morse boundaries. And these mostly appear in the original papers of myself and Sultan, a couple of papers by Matt Cordes, Devin Murray, Ching Liu. I'll mention some other names later, but the properties I'm going to talk about here were in the first few papers on these Morse boundaries, because this was the whole reason for introducing them. All right, was to see if we could get these properties working. Okay, so let's go through the list of properties. I've added a property 0 here, which wasn't before. Hyperbolic boundaries were only defined for hyperbolic space, and okay, it turns out you could define it for cat 0 space. They just didn't behave very well. So the first observation is we've now defined a boundary that makes sense for any geodesic metric space. I didn't explain this, but it turns out even trying to define a topology on the set of rays, if you don't have the Morse property, is difficult. You can't even define the boundary in general if you don't have the Morse property. So the first thing is that this is a well-defined metric space. Okay, sorry, not metric space, a well-defined topological space. Take that back. Well-defined topological space that makes sense for any metric space. All right. Okay. So now let's go on to the list of properties we had for hyperbolic boundaries. The first property we had was that the boundary was compact and metrizable. Well, we don't quite have that. It turns out that the n Morse boundary is compact and metrizable for any n, but we lose that often when we take the direct limit. That's no longer true. I'd like to argue, some people, this upsets some people. Oh no, space is not metrizable. But I would like to say that my view of this is it doesn't matter that much, because when you're working with a direct limit space, generally you prove properties at the finite stages and then just say, okay, if it works at every finite stage, then it works in the direct limit. So at least we have these nice finite stage pieces that are compact, metrizable, understandable, et cetera, et cetera. Okay, so yes, compact, metrizable at the finite stages, but not at the direct limit stage. Okay, visibility property. I stand on two places on the Morse boundary. Can I see them from each other? And the answer is yes, it holds. In fact, well, let's just leave it at that. So the visibility property holds for any 2 points on the Morse boundary. Can always connect them by a bi-infinite Morse geodesic. Okay, what about dynamics? Yes, the dynamics are nice. Any infinite order isometry, the induced map on the boundary fixes at most 2 points. We can classify things by whether they fix 0, 1, or 2 points. So great. And finally, and this I don't know, most importantly, but at least this was a lot of the motivation behind defining these spaces. We have a quasi-isometry between two spaces does indeed induce a homeomorphism on the Morse boundaries. Okay, so in particular, we can define the Morse. Oh, I didn't even write it in here, but this means that the Morse boundary of a group is well defined, of any finitely generated group. We can just take the Morse boundary of its Cayley graph. Okay, so quasi-isometry invariance means we can apply this to groups and talk about the Morse boundary of a group. Not only that, there are some partial converses of this, which I'm not going to go into in detail, but similar to the case of the hyperbolic boundary, if you add some additional conditions on F, you can get back the other way. If you add some additional conditions on this side, you can get back to the original quasi-isometry. Okay, so all of those properties, more or less, almost all of those properties now work. Okay, all right, great. There's lots of other properties. I'd be here all day if I tried to tell you all the nice things that these boundaries satisfy. There's papers by Cordes, Hume, Durham, Abdul, Zaloom, Liu, Tran, Incerti, Medici, Russell, Briano, Kerr, et cetera, et cetera, et cetera. People have really been looking into these boundaries in some detail and proved in some cases just doing some interesting computations of what the boundaries look like. In other cases, establishing more interesting properties. So there's lots and lots more I could say if I had time. All right, I'm just sticking to the basic motivating properties that we looked at. All right, okay, so that's exciting. But of course, what I've focused on is the nice properties of the boundary. It turns out there's some not so nice properties of this boundary. And let's list a few of these because it's motivation for the next step. So the not so nice properties is, first of all, as we already saw, sometimes it's just plain empty. And while actually that's still a quasi-isometry invariant, that is, if two spaces are quasi-isometric and one of them has empty Morse boundary, then the other one has empty Morse boundary. But other than that, it's not terribly useful if it's empty. All right, so that's one bad piece of bad news. The other, as I already pointed out, if we pass to the direct limit, the topology can become pretty strange. Like in general, if X is not hyperbolic itself, then it's not going to be compact. It's not going to be metrizable. It's pretty awful if you try and work. It works fine if you work in the N Morse boundary, but if you pass to the direct limit, things get pretty strange. Okay, so maybe that's not so good. And I think maybe most importantly, at least with respect to what we're going to hear about this week, is that there are just way too many rays that it doesn't accept. We throw out an awful lot of information, and we throw out so much information that it turns out that there's no kind of nice measure you can put on these, and we do not get a model for the Poisson boundary. So I have not told you about the Poisson boundary other than it sort of comes out of doing things like random walks. We're going to be hearing all about that, and while it's defined as a measure theoretic object, it's nice to have a good topological model for these Poisson boundaries. And it turns out that this Morse boundary just doesn't have enough stuff in it to give you a topological model for the Poisson boundary. And that's unfortunate. All right, so these are some of the properties that, are not, we wish we had, okay? So let's fix it. That brings us to the sublinear Morse boundary. So the idea here, did I put who names? I don't know. Yeah, this is due to Ching, Rafi, Tiozzo, and Zalum also has some contributions to this. They came up with the following idea, which was, what if we loosen up the Morse property a little bit? So instead of requiring that all our arrays be Morse in the sense that I defined, what if we allowed for something a little more general than that? Could we still get a lot of the nice properties of Morse boundaries, but see more of the space, allow for more geodesics than we had before? Okay, so here's what they did. They said, instead of requiring geodesics to be Morse, let's just require them to be sublinearly Morse. So I'm going to leave it to Khazra Rafi to give a really formal definition of sublinearly Morse. I'm going to give you an intuitive definition, intuitive idea of what it means to be sublinearly Morse, and leave the formal definitions to Khazra. So what was Morse? Let's remember, we had a lambda and an epsilon, and given a lambda and epsilon, we had a constant n, such that given any lambda epsilon quasi-geodesic that began and ended on alpha, we knew no matter where we put that. So let me add to this. Maybe there's another beta over here and another beta over here. But any lambda epsilon quasi-geodesic, they would always stay within n, no matter where they lived, and no matter how long they were. If they began and ended on alpha, they stayed within distance n of alpha. Yeah, that's Morse. That's n Morse. Okay. Sublinearly Morse, we get to take into account how far away beta is from our base point. All right. So intuitively, as I said, this isn't a formal definition, but here's the idea. We take a sublinear increasing function kappa. So it's an increasing function, but if we graph kappa, it increases slower than linear. Okay, it's like a log function or something like that. Okay, so a sublinearly increasing function, and now the bound on how far away beta gets from alpha can depend on how far we are from the base point. So if I'm back here, I have to stay closer, whereas if I'm way out here, I get to go farther away, because this is less than or equal to not n, but n times kappa, and kappa is growing, where this is r now, right? So the farther away I get, the more I can diverge from my geodesic. It's just that divergence, that thing that measures how far I'm diverging, has to be sublinear. Okay, as I said, the formal definition is a little different, but this is the intuition, okay, is that I loosen up my Morse constant the farther away I get from my base point, okay? So hopefully, at least you've got sort of an intuitive idea of what a sublinearly Morse geodesic is. And actually, they need sublinearly Morse quasi-geodesics as well. But let's just leave it at that. The basic idea is I'm now going to construct a boundary which allows for these sublinearly Morse things. Oh, let's go back to our example for a minute while we think about what sublinearly Morse means. Okay, our tree of flats. What do we need? Well, we no longer need to stay so to be Morse, there had to be some bound like C, such that every segment inside a flat had length less than C, less than or equal to C. There was a bound on how long we could stay in the flat. Well, there's still bounds on how long we could stay in the flat, but those bounds can grow the farther and farther away we get. So the first one, we can stay distance C, the second one, a slightly bigger C, a slightly bigger C, a slightly bigger C, as long as that growth is sublinear, yes, in terms of how far away we are. So we get a lot more geodesics than we had before. There's no uniform bound anymore. It just has to grow sublinearly. Okay, so that there's an example of where you can see that this allows for a lot more geodesics. Okay, so what they do is they construct a boundary that now allows for kappa Morse geodesics instead of just Morse geodesics. And it turns out, they then prove that this boundary has all the nice properties we had before for the Morse geodesic, but now it has a lot more. In particular, I mean, we'll be hearing about that, I assume, lots of properties in Kasra's mini course. In particular, it's going to provide that connection with the Poisson boundary. It's going to give you a model for the Poisson boundary. So it's going to connect the two different types of boundaries for us. Since we have a whole mini course on this, I am not going to go into any more detail today. I'm going to leave that for Kasra. And